I'm gonna be talking about Siamese recurrent architectures for learning sentence similarity in 2016, and this is a positive example. So we present a Siamese adaptation of the long short-term memory network for labeled data comprised of pairs of variable length sequences. Our model is applied to assess semantic similarity between sentences, where we exceed state-of-the-art outperforming carefully handcrafted features and recently proposed neural network systems of greater complexity. And for these applications, we provide word embedding vectors supplemented with synonymic information to the LSTM, which use a fixed vector to encode the underlying meaning expressed in the sentence, irrespective of the particular word. By restricting subsequent operations to rely on a simple Manhattan metric, we compel the sentence representations learned by our model to form a highly structured space whose geometry reflects complex semantic relationships. So we just use this Manhattan LSTM that you see here is LSTM for one sentence and another for another sentence, and you see the measure of similarity. They use Manhattan distance, and the LSTM learns the mapping from space of variable length sequences into RD representation. So from 300 dimension we go to 50. And the final representation is encoded by HD. So unlike typical language model, RNNs, which are used to predict the next word or token, our LSTM simply functions like the encoder of this article, like thus the sole error signal backpropagated during training stems from similarity between the sentence representations. And of course, these ideas avoids those anisotropic phenomena that happens in classical networks. So we restrict ourselves to the simple similarity function, this one, and you can implement it using this function. So we use the sum of torch, the sum function, and then we use the absolute value of two vectors and we exponentiate it. But there is a warning. They pointed out using L2 rather than L1 norm can lead to undesirable plateau in the overall objective. So this is because during early stages of learning, an L2 based model is unable to correct errors where it is erroneously believed semantically different sentences to be nearly identical. So that's why L1 norm is much better. And for stick data contains 9,000 sentences, which you can see the skip gradient, thought, and the MA-LSTM predictions for different sentence pairs. But here is important, because LSTMs typically require large datasets to achieve good generalization due to the vast number of parameters, and we thus augment our dataset with numerous additional training examples as well as high-performing neural networks. So this MAS LSTM predicts the relatedness for a given pair of sentences by G, and we train this Siamese network using backpropagation through time under the mean squared error loss. So this LSTM uses 50-dimensional hidden representation, and optimization of the parameter is done using this method in 2012. And of course, they use gradient clipping because we clip the gradient if it is too high. We don't want to move suddenly end with high values and go to another point. So it becomes very high. I mean, the frequency increases if we do so. In order to reduce this frequency during learning, we use gradient clipping, which is a very good approach to deal with this problem. So it is well known that the success of LSTMs depends crucially on their initialization, and often parameters transferred from neural networks trained for a different task can serve as a strong starting point for optimization. Well, we first initialize our LSTM weights with small random Gaussian entries. Then our MALSTM is pre-trained as previously described on separate sentence pair data provided the earlier SEM-eval 2013. The weights resulting from this thus form our starting point for the SIG data. So because all of these are important, because the initialization is very important step in for a good training of LSTM. And you see the error for different methods, and for the MALSTM the error is reduced in comparison to previous methods. And also they have tried it with 3LSTM model as well, comparing sentences. And this is MALSTM representations of test set sentences depicted along 3 different dimensions. So each number above the axis corresponds to a sentence representation, and its location represents the value this particular hidden unit assigns to the sentence.